So this is a fantastic audience. I'm just humbled by the range of perspectives and expertise that are in this room today. I'm going to be representing a particular point of view, which is part of the research community on electronic voting in computer science, and there's actually a thriving research community. We have multiple annual workshops about new results in electronic voting related technology, and I should put in a plug for this summer's electronic voting technology workshop, which is going to be held in Seattle, Washington in August, together with the Usenet Security Conference, and I happen to be co-chair of that workshop. So you should all come, technologists and non-technologists alike. But today I'm going to be talking about a few stories that represent data points from what we've learned in the technology research community about the properties of electronic voting systems that have actually been deployed or were very close to deployment when we got a chance to look at them. And by and large, electronic voting in the US has happened without input from science. It's been something where vendors have produced systems, sold them to election officials, and then only afterwards have independent researchers had a chance to examine the systems and figure out whether they lived up to the claims that were being made about them. One of the first chances that the research community had to do with this, it should be a system that's familiar to people who are visiting from Maryland, and that's the Diebold AccuVote TS system. And in 2006, my colleagues at Princeton and I had the chance to examine one of these systems and do the first independent academic security review of a machine like this, where the academics were able to speak about what they found in public. We acquired the machine under very interesting circumstances because Diebold has had a long history of secrecy, trying to avoid public scrutiny of their technology. But we were given a machine by an anonymous source that our lawyers assured us was able to give us the machines. But I actually had to go up to New York City, and this is like something from a spy novel. I double parked in a white sedan outside a Times Square hotel, and then went into the alleyway behind the hotel where a man in a trench coat gave me a black leather suitcase containing the voting machine. Anyway, we took it apart and reverse engineered it and found out how it worked and how the software worked. And after we had done that, it was pretty clear that it had some undesirable security properties. So what we did at the end of the day was we produced a demonstration of what an attacker could do. So we had a mock election, George Washington versus Benedict Arnold. And in our mock election, we'd have, say, 5 votes for George Washington, because who would vote for Benedict Arnold? But then we'd press the total button at the end of the day, have the machine print out the results, and here's what it would print: Benedict Arnold wins by 1 vote. And that's because we figured out that it was very easy for malicious software, if installed on the machine, to affect the outcome of the election. And this is the software we've produced. You can just use the touchscreen to choose the election outcome. All the records of the election are stored in the machine's memory and tamperable by software. It would take less than a minute of access to the machine or its memory card to install software like this. Just put a memory card in the slot and you're done. And furthermore, we found that we could create a voting machine virus that would spread from machine to machine during normal election activities and change votes in all the machines in an entire state. This is scary stuff. But it's not just one vendor's machine. In later studies like the California top-to-bottom review, where academics were invited to examine the source code to all of the electronic voting machines used in California, we found that every single one of the touchscreen voting machines had similar kinds of problems to this, that the votes could be tampered with, that the election outcome could potentially be changed by malicious software. Eventually, after years and years of doing this, and however many different voting systems that fell prey to this, it ended up being not so scientifically interesting, just more of something to do for fun. So when a couple of years ago, when a colleague at Princeton and I got access to a Sequoia ABC Advantage machine, another touchscreen voting machine used in different parts of the US, we took it apart and decided to have some fun with it instead. We noticed that inside it was like all other electronic voting machines, it's just a computer. But this one was even more similar to a desktop computer than some others. It's just a 486 chip for the geeks in the room and a little compact flash memory card containing the software. So like any good geeks, we did what geeks would do in this sort of situation. We made it run Linux, first of all. And then after we were done with that, we wanted to have some more fun, so we made it into a Pac-Man machine. Here it is running the original 1980s Pac-Man, and it's still doing that in the lobby of the Princeton Center for Information Technology Policy today. The implication being, if we can modify the software to make it run Pac-Man, of course we can modify the software to make it steal votes. But what I want to talk to you for most of my time today about is the Washington, D.C. internet voting system. Because while polling place voting systems are something that we understand pretty well now, most states now realize that the minimum you need to ensure that these systems are working safely is to have a paper trail that you can audit. But the next wave, at least in the US, is clearly going to be internet voting and the question of whether states should allow votes to be cast online. Internet voting presents a whole new set of challenges, but we're only beginning to get interesting data points about how the security of these systems looks in practice. But Washington, D.C., before the 2010 general election, decided they wanted to field a trial internet voting system to allow overseas and absentee voters to cast their votes online. The DC trial was very good in that the government went to the research community and asked, first of all, how can we do this securely? And what most of the scientists they talked to told them is, no, don't do this. You can't do it securely. The technology is not ready yet. But the DC decided to go ahead with the system anyway. But one great thing they did was they decided to hold a public trial where they, for a week, a few days before the election was to begin, they held a mock election and invited anyone who wanted to, from the public at large, to try to hack in and change the results. Now, it's not every day that you're invited to hack into government computers without going to jail, so I just couldn't resist this opportunity, and I recruited a team that included two of my PhD students at Michigan and a member of our technical staff to try to participate in the trial. Now, DC made a lot of information available, which made for a much more realistic trial. You know, in a real election, an attacker could break into systems and steal source code. They could coerce people into giving them a copy of the software and so forth. We couldn't commit crimes. So to make for a realistic trial, DC provided their source code in an open source format, and they provided a map of their network that said what range of computers we could examine in the test. So we did that. We looked at the software. Here's just a brief 2-second run through the software. The voter logs in using personal identification numbers sent to them in the paper postal mail. They download a blank ballot. Comes as a PDF. They select the candidates they want to vote for in a PDF reader, save the file, upload it back to the system, and it gives them this thank you page where they're invited to tell everyone they voted on Facebook and Twitter. So this looks good, and actually it was a really well-designed system. Compared to the polling place electronic voting systems I've looked at, and I've evaluated the source code to many of them, this was much better engineered. It was done by people who knew what they were doing. It was using the latest modern web standards and so forth. But we started reading the source code, and it's a big, complicated program, and complicated programs have bugs. And after a few hours of reading the source code, my students and I found a bug. The bug is on this line right here. They're using double quotes instead of single quotes. This allowed us to steal the election. So we also found some interesting things on their network, including a system with a default password. And because they hadn't changed the password for one of the network boxes, the password in the owner's manual still worked. And we were able to use this to get into some of their lower level network systems, their routers and switches. Beyond that, we found these great network security cameras in their server room that let us see the systems, let us see the sysadmins, and let us know whether our attack had been detected, because we could tell whether they were just perfectly calm, here's the night watchman, or whether after they detected the attack they looked quite a bit less happy with us. So we waited until after, we used this to learn their habits, and then we waited until after 5 o'clock when they seemed to go home every night, just in case they were actively watching the system. And then we used these different problems in these different holes in the security armor to try to simulate what a real attacker might do when faced with a real election. So the first thing we did, we took all the data we could that would help us maintain our holes into the system, any credentials, keys, etc. So once an attacker gets into your system, it's much harder to get them out again than it is to keep them out. That you're in a much worse security position than you were before, even if you reset the system. After that, second thing we did was we changed all the votes. So we replaced all the ballots that had been voted so far by other testers with our own ballots that consisted of write-in candidates, and you can't quite see because of the focus, but these are evil robots and artificial intelligence from the movies and science fiction. Basically, what would the computer vote for if it was in charge of who won the election? Because really, you are trusting the computer to be in charge. If the computer is incorrect, if it's behaving erroneously, or if it's been reprogrammed to behave maliciously, it can change the outcome. So after we changed all the votes, we rigged the system to replace any subsequent votes with our own candidates. We added a back door that would let us know who you voted for, so violating your secret ballot. We cleared the logs and cleaned out all cleared our tracks. And then there was one more thing we wanted to test, which was how well would election officials respond? Because there are very, very few cases where we've had a penetration test like this that was online where the voting officials didn't know whether anyone was going to get into the system or not. Would they be able to detect our attack? Would they be able to recover from it? But because the real election was supposed to start about a week later, we didn't want to wait until the very end to see if they found it, so to just give them a little bit of a heads up, we left a calling card. And our calling card was that we changed that thank you page at the end so that after a delay of 10 or 15 seconds, the voter's computer would start playing the University of Michigan fight song, Hail to the Victors. Even with this calling card in place, it was still 2 days before the election officials realized anything was wrong, and that was only because another person testing the system wrote to them and said, "It looks okay to me, but I don't like the music that plays at the end. It's too distracting." So after DC officials found out, after they learned about the attack that way, they, in my mind, correctly decided to call off using internet voting for ballot return in the real election. The technology just wasn't ready. Instead, they did something much more sensible, which was to allow people to download a blank ballot via the web and then send it back in the mail. There's not a central point of failure in quite the same way. The security risks are much more well known and well understood. So let me conclude with a couple of remarks about internet voting and electronic voting generally. First, that transparency and software independence are the key to making e-voting trustworthy. Transparency means the system is observable by people. We don't have to depend on black box processes that people can't understand in order to understand whether the vote's correct. Software independence is a more technical property that was defined by Ron Rivest at MIT that explains that errors in the software or malicious behavior by the software must be things that we are guaranteed to be able to catch and be able to detect that something is wrong. One way to provide this is with paper ballots that you can audit at the end of the election. The second point is more about internet voting, which is that in order to do internet voting securely, I think we're going to have to solve some of the most difficult problems in computer security. How do you keep servers from being attacked remotely? And Google, the Pentagon, Facebook, all these companies with huge budgets for protecting against attacks have fallen victim to remote intrusion in recent years. There's just no way that municipalities are going to get this right. We have to protect the clients from malware, from spyware. And we have to prevent phishing attacks where the voter's just convinced to vote in the wrong place. All of these, some of the biggest open problems in computer security, and they together lead me to believe that it's going to be decades, if ever, before we're able to vote online securely. Thank you very much.